Good afternoon, ma'am.
Good afternoon. So let's see one example related to the Heaviside function. Then we'll discuss about the Dirac delta function. Question is very simple question. Then I'll write some questions for your practice. Solve y double dash plus 9y is equals to Heaviside of t minus 3, y0 value is 0 and y dash 0 is 0. This is the simplest question. Okay. Now we'll take the Laplace transform of both the sides. Laplace transform both sides. Nine into Laplace transformation of u of t minus 3. Okay. So you know the formula. S square Laplace transformation of y, s y at 0 and y dash is 0. Then 9 of Laplace transformation of y. 9, you know the formula, e power minus as over s, Laplace transformation of u of t minus a. Okay. So if you remember in the first day when we have started this Laplace transform, we have seen the second shifting theorem. There was a Heaviside function in that. So at that time I told you like we'll discuss later when we discuss about the Heaviside function. Okay, so it was f of t minus a and u of t minus a Heaviside, e power minus as fs. Okay, so fs means corresponding ft, where fs is nothing but Laplace transformation of ft. Okay, and in the same manner we can define inverse Laplace transform, L inverse of this. You'll always get f of t minus a and u of t minus a, where ft is this. Means just take the inverse Laplace transform here, ft you will get L inverse of fs, and then replace t by t minus a, you will get the. So this is very important. Please remember these two properties when we have simply the Laplace transform and when we have its inverse, corresponding inverse. Very important. Now let's come here. This is 0, this is 0. So Laplace transform of y is nothing but s square plus 9. Okay, so when you have this type of situation, exponential and numerator, so take 9 e power minus 3s outside and 1 by s square plus 9 inside. This is Laplace transformation of y. So we use partial fraction here, partial fraction of this, and then you know how to use partial fraction. I'll write here, then I will erase. Okay, so if you want to note it down, you can note down. That means a over s, and when we have for this factor a over s, for this factor when we have quadratic term, so bs plus c. So take LCM, s into this, that means bs square plus cs. Now compare the coefficient of s square, s and constant term. So when we are comparing the coefficient of s square, you will get this and this. A plus b is equals to 0. Comparing the coefficient of constant term, only one constant term means 9a is equals to 1. That means a is equals to 1 by 9. From here, b is equals to minus 1 by 9. Now comparing the coefficient of s, you will get c is equals to 0. Okay, that means here if I'll take eraser, a value is 1 by 9, b value is minus 1 by 9 and c is totally 0. Okay, so 1 by 9 minus 1 by 9. So it is the partial fraction of this. That means 9 e power minus 3s 1 by 9s minus 1 by 9 s square plus 9. But this is s here. Okay, this 9, this 9, this 9 you can cancel. So I'll erase this, this and this. Now this is Laplace transform of y. That means y is equals to L inverse of this. So I'll erase this now, this calculation part. Now here we use second shifting theorem. This is nothing but Laplace inverse of e power minus 3s 1 by s. Then minus L inverse of e power minus 3s and this s over s square plus 9. Okay, see e power minus as fs. So for first term I am writing fs is 1 by s. So ft will be Laplace inverse of this 1 by s. That means 1. Okay, now if I'll solve only first term, f of t minus a. So if it is not containing t, how will you replace t? So let's just write only this. F of t minus a means simply 1. T minus a, u of t minus a. A is 3 here. So u of t minus 3. So first term, by solving this, you will get this. Now I'm solving second term. Fs is s over s square plus 9, right? So ft will be L inverse of this. That means cos 3t. Right? Now if you are solving this, e power minus as fs is equals to ft minus a. Ft is this. A value is this, 3. So you need to replace t by t minus 3. That means minus this minus f of t minus 3. So that means cos 3 and t will replace by t minus 3. Just replace t. U of t minus 3. So this is your value of y. This is how you can use shifting theorem. Okay. Now there may be more complicated questions that you need to solve because everything depends on Laplace inverse and Laplace transform. If you remember the concepts, if you remember how to solve, then to solve differential equation is not that big task. Okay. But here in your syllabuses, we need to solve the differential equation. And because Laplace transforms already you have studied in calculus for engineers in the detailed form. So this should be understood that you all are having the knowledge for that, for Laplace transform. And if you don't remember, please go through any book or basic concepts of this. So I'll write some questions for you. that you need to, just for your practice purpose, not that difficult question I'll take. Find the solution. Solve y double dash minus 6y dash plus 5y is equals to ft. ft, where ft is t minus 1 when t lying between 1 to 2 and 0 otherwise. So when you take Laplace transform and when you are writing Laplace transform of ft, either you can use Heaviside function to write it in the component form, in the addition form, or simply you can use the definition of Laplace transform, like 0 to infinity. So first 0 to 1, this value, sorry, 0 to 1, 0, then 1 to 2, this value, then 2 to infinity, 0. That means you need to solve the integration from 1 to 2 only. E power minus st, ft is t minus 1 dt. Okay, and if you want, you can write ft as first, because anyhow when we are taking Laplace transform, you need to find Laplace of ft, right? So either you can use definition or you can write ft as, see, u of t minus 1 minus u of t minus 2 multiplied by t minus 1, right? Then 0 into, you can say that it is for t greater than 2, so u of t minus 2, like that. That means simply you have this, ft is equals to u of t minus 1 and t minus 1 minus t minus 1 and u of t minus 2. Now you need to take Laplace transformation of ft. So Laplace of t minus 1 and u of t minus 1. Laplace of t minus 1 and u of t minus 2. See the shifting theorem, f of t minus 1, t minus a, u of t minus a. Why I am writing so worse? Laplace transformation of f of t minus a and u of t minus a is equals to e power minus as and fs, right? See, t minus 1, ut minus 1. T minus 1, t minus 1. Same, right? T minus a, t minus a. So e power a value is 1 here. That means minus s. Fs is, so for this, ft is simply t. Then only t minus 1, right? So Fs you will get 1 by s square, right? So first term is this. Now this. To use shifting theorem, it should be 2, right? So we can adjust like t. We can add and subtract 1 and 1. So you'll get t minus 2 minus 1. Sorry, minus add plus 1. This term you can write, right? And u of t minus 2. This term as it is. See, you can multiply this Heaviside function into t minus 2 and this into this, right? So Laplace transformation of t minus 2, u of t minus 2. Then minus minus plus, so plus of Laplace transform of u of t minus 2. Simply when u of t minus 2 is multiplied here. Again, the same formula, right? Here. So I'll write first term e power minus s over s square. Take y0 and y dash 0, both are 0. E power minus s over s square minus Here e power minus 2s over s square, because it is a is 2 here. Now here e power minus as means 2s divided by s, simply the Heaviside function. So this is your RHS. Solve for LHS also, collect the coefficient of Ly, then take inverse Laplace transform, and then you need to use the inverse Laplace transform in second shifting theorem. Okay, so that I have given you hint how to proceed. Now you can complete this question. So today main topic is Dirac delta function. So to go directly to the Dirac delta function, we have unit impulse function. Like unit step function or Heaviside function, now unit impulse function. So unit impulse function means, as from the word itself we can understand that the idea of very large force acting for a very short time is of frequent occurrence in mechanics. Okay, so the idea of very large force acting for a very short time is of frequent occurrence in mechanics means for example, like in real life, when you hit a wall by a ball, okay, so the impulse of the force that hits that wall is of very short time, even for the microsecond it will hit the wall, okay, or it will hit the surface. So that force is that force you can understand as the impulse function, unit impulse function. So the unit impulse function is considered as the limit form of this function. So the unit impulse function is considered as the limit form of the function, this delta epsilon, notation is this t minus a. So its value is 1 by epsilon when t lying between a to a plus epsilon. Okay, where epsilon is just a positive number but very small, like 0.00 something. See, a and a plus epsilon, t means of in a very short time it is defined as 1 by epsilon and its value is 0 otherwise. So the unit impulse function is nothing but the limit form of this. Limit form of this means if we'll take epsilon tends to 0, the function you will get will be defined as unit impulse function. Okay, so let us see by the graph. Suppose a is here, and just to differentiate between the lines, let's take a plus epsilon is here. It's very short difference between a and a plus epsilon. Okay, you can consider epsilon as 0.000 something like that. Okay, so but we need to make a difference. So that's why. So its value a plus epsilon when t lies between here to here, and because the boundary includes, its value is 1 by epsilon. Let us say 1 by epsilon is somewhere here. Okay, t, and this function defined on y-axis is t minus a. Now you can see that as epsilon tending to 0, epsilon tends to 0 means epsilon is tending to 0. That means these 2 points, epsilon, a plus epsilon, and epsilon tends to 0. That means this point is approaching to a. Approaching to a, that means the difference between a and epsilon is becoming 0, or it is becoming only a 1 point. So when epsilon tending to 0, it is coming to this and this 1 by epsilon. Epsilon tending to 0, the height of this will tending to infinity, or will tend to infinity, right? So as epsilon tends to 0, it is clear that the height of the strip increases indefinitely and the width decreases. The height of the strip increases indefinitely and the width decreases. Okay, so means if you are taking epsilon tending to 0 in this function, you will get a Dirac delta function. That's it. Thus the unit impulse function or Dirac delta function is defined as thus the unit impulse function delta t minus a, or you can say that Dirac delta function is delta t minus a is infinity when t is equals to a, and for otherwise means when t is not equal to a, its value is 0. Okay, from the previous graph you know that this was the strip, so a plus epsilon. So when epsilon tends to 0, only one point you will get, that is t is equals to a, and t is equals to a, it was defined by 1 by epsilon, right? So its value is infinity. That means Dirac delta function is nothing but limit epsilon tend to 0 in Dirac this function. So when epsilon tends to 0, you will get Dirac delta function, right? So this is Dirac delta function. Now here arises the question of Laplace transform of this. Now Laplace transform of this means directly we need to substitute infinity, right? And t is equals to a. So we'll find Laplace transform of delta t minus a. That means take here this limit epsilon tends to 0 and Laplace transform of this t minus a. That means first find this, then substitute here, and then take epsilon tends to 0. That's it. So from here itself we are writing, and because Laplace transform is a linear operator, that's why we are multiplied inside. We are not multiplied inside. We have interchanged the order of limit and Laplace transform. Okay, so it is not like we are multiplying inside. It is like we have changed the, because it is the limiting case and linear operator. This L is a linear operator. So first you can take the Laplace transform and then limit. Both will be same. So let's find Laplace transform of this. Now it was defined from 0 to a, like 0 to infinity the whole interval is. So let's break that. 0 to a, its value is, so if you remember that a to a plus epsilon, its value is 1 by epsilon, and otherwise 0. So a to a plus epsilon, that means 0 to a, its value is 0, e power minus st dt. Then a to a plus epsilon, its value is 1 by epsilon, e power minus st dt. Then a plus epsilon to infinity, its value is 0, e power minus st dt. Okay, that means only this is 0, this is 0, so we need to calculate this. One by epsilon is independent of t, so you can take outside, right? Now e power minus st integration is e power minus st divided by s and minus, and the limits a to a plus epsilon. So that means you can take s also outside, because we need to substitute limit for t. Upper limit, that means in place of t only, e power minus s a plus epsilon, minus lower limit, that means as. This. Okay, so a plus epsilon minus s and this. Okay, now this is your this value. Now we need to take the limit. So I'll take next page. So it was limit epsilon tend to 0. Now I'm directly writing the Laplace transform of Dirac delta function. Minus epsilon s, and it was sa plus this. Okay, e power minus as, then you can write down in this form. Epsilon s, okay, minus e power minus as. So you can take e power minus as outside. Epsilon s, then e power epsilon s minus 1. Why I'm writing infinity? It should be 0. Zero, zero, zero. Okay, so exponential formula: 1 plus x square by factorial 2 plus x cube by factorial 3. So 1 plus x, that means epsilon s, plus x square by factorial 2 by factorial 3, and so on. That minus 1. So minus 1 and minus 1 cancel, right? Limit epsilon tend to 0. This epsilon will, you can multiply inside. So this will cancel. 1 power will cancel. 1 power will cancel. So you will get 2 2. That means e power minus as so okay. That means you will get epsilon s, epsilon square s square 1 plus, sorry, because cancel. Okay, so it was factorial 3, it was factorial 2, and so on. So when you take epsilon tends to 0, see, except this term, all will tends to 0, right? So here you will get e power minus as. Now I'm getting confusion, like minus. I think I have mistaken somewhere. There should not be any minus here. So you please check your calculation. Means check my calculation, or you can try by yourself. Laplace transform of Dirac delta function is simply e power minus as. Okay, suppose you need to find Laplace transform of Dirac of t minus 2. Simply you can write e power minus 2s. And in unit step function, it was divided by 2. Sorry, divided by s. Okay. I'll check the calculation. I think I have mistaken somewhere. It should be e power minus as only. Okay, so in next class, we'll discuss example related to this. Then this is your 4th module. So we have the system of equations now. System of differential equations. Okay, so that we'll discuss in next class, and some application based questions like application in ERC circuit or LRC circuit, we'll discuss it. And in spring damped motion. So that we'll discuss in next class. Any doubt in this? Please you try this question, this Laplace transform of Dirac delta function by yourself. But the proof is not in your syllabus. You need to remember the term, final term. I think I have mistaken somewhere in minus term. So you can go through it and you can check the calculation. Any doubts?
No, ma'am.
Okay then. Please mark your attention, everybody. And those who have marked their attendance,
Ma'am, when is the quiz?
maybe next weekend. Not coming, next